Lesson 19 is on inverse trig functions. So a one-to-one function is a function that has a unique inverse, and because of this, it passes the horizontal line test. So we've talked before about the vertical line test. The vertical line test tells whether or not something's a function. The horizontal line test tells whether its inverse is a function. Okay, so if you think about some basic functions, the first one we'll talk about is y equals x cubed. Yes, it's a function because it passes the vertical line test, right? But its inverse is a function because it passes the horizontal line test. So if you found the inverse by switching your x and y and you solve for the new y, y inverse would equal the cube root of x. Okay, and that is also a function. The cube root of x looks like this, so it passes the vertical line test. All right, but if we have y equals x squared, right, this does not pass the horizontal line test. That's because if I have the point 2,4 and the point negative 2,4, when I talk about its inverse, I would have the point 4, 2, but I'd also have 4, negative 2. Okay, and that's not good. That creates a problem that's on its side, which is not a function because it doesn't pass that vertical line test. Okay, so what we want in order to define the inverse is for there to be a unique inverse. Okay, so there's not going to be like a plus or minus or anything. It's just going to be just one function. So with sine and cosine don't pass the vertical or the horizontal line test. So we need to think about portions of them that do. Okay, so if we sketch out sine, it starts at 0, 0, goes up and then down, right? That was a little struggling over there. So as we talk about where it does pass the horizontal line test, it passes it right here. Okay, so if you notice that if you draw a horizontal line through it on that entire interval, we're good. But as soon as you go outside of that interval, if you went back down just a little bit, it doesn't pass that horizontal line test. Okay, so this interval is important to us. This is where if you use inverse sine, so sine to the negative 1 on your calculator, every single answer will be between negative pi over 2 and pi over 2. Okay, so every number will be between negative 1.57 and positive 1.57 that your calculator is giving you. Okay, and what I always like to think of, since I am a fan of the unit circle, you know it, I always think about the right side of the unit circle. So we're going between negative pi over 2 and pi over 2. Okay. So it says this graph passes the horizontal line test, therefore there's a unique inverse. This inverse function is called the inverse sine function, which is denoted by inverse sine of x, which you've seen in your calculator, or you might also see arc sine of x. Okay, that's just kind of an old notation, probably because typewriters couldn't do like raised to the negative 1, so we did arc sine, right? But it makes sense when you think about the unit circle because it is just an arc of a circle. Okay, so all right, so it says obviously there are an infinite number of x values, so that f of x equals sine of x. For instance, there are an infinite number of x values for which sine of x is equal to 1. If you think about all the places where sine of x is equal to 1, well, it would be at pi over 2, but it'd also be at 5 pi over 2, 9 pi over 2. Every time you rotate around, you get another value. And therefore, when we find inverse sine of 1, so if you find it on your calculator, you're going to get only one answer. It's not going to give you an infinite number of solutions. It's going to give you the one answer that's on this interval. So your calculator would give you the answer pi over 2 or 1.57, whatever. Okay, it says the inverse sine function is defined by y equals inverse sine of x if and only if sine of y equals x. Okay, so what you're really thinking is that if you have inverse sine, then we want, so if I have inverse sine of root 3 over 2, then I want to find the angle, right? I'm solving for the opposite. I'm finding the angle that gives me a y value of root 3 over 2. So that's how I want you to think of it. So you can always say equals theta and then rewrite it. So you have sine of theta equals root 3 over 2. But when you think about it, I don't want to get you to give me an infinite number of solutions. I only want you to give me the answer, the one single answer between negative pi over 2 and pi over 2. So where is sine of theta equal to root 3 over 2? It would be right here. So theta would equal pi over 3. So what that means is that inverse sine of root 3 over 2, it's saying what angle gives you a sine value of root 3 over 2? The only angle on that interval is pi over 3. So that's our answer. So it's really not too terrible. You're just kind of thinking backwards. So if I have inverse sine of -1, I want you to think only on that interval, -π/2 to π/2. So where is sine equal to -1? It's right down here. So be careful, don't call it 3π/2, we call it -π/2. So for that same reason, we have explained why inverse sine of sine of π/4 is π/4, but inverse sine of 7π/4 is not equal to 7π/4. Okay, so when you get these types of problems, and this is always frustrating when I was in math, because I was like, I just want to just cancel those out. I just want to say, yeah, it's π/4. Yes, this is 7π/4. But your calculator even will not, it will not give you that this second one is true. It will not work. Okay, so why is that? We work from the inside out. So if we have sine of π/4, right, here's where π/4 is, that's root 2 over 2, right? So we have inverse sine of, working from the inside, really root 2 over 2. Well, inverse sine of root 2 over 2, if I think about the right side of the unit circle, and I'm between -π/2 and π/2, it's right there. It's π/4. But if I do the second problem, and I think about sine of 7π/4, 7π/4 is in the fourth quadrant. Okay, its sine value is -root 2 over 2. So we're going to get inverse sine of -root 2 over 2. But then when we think on that restricted interval, -π/2 to π/2, yes, it's in that same location. I get it. You want to say 7π/4, but it's not 7π/4. Okay, it's not 7π/4 because your answer has to be between -π/2 and π/2. So it's not it's not 7π/4, it's -π/4. So basically it kind of goes back to coterminal angles. Coterminal angles are angles that are in the same location but are different measurements, right? Like -π/4 is the same as 7π/4. Okay, so we don't write 7π/4, we write the number that is between -π/2 and π/2. So they don't exactly cancel, you just have to change it based on the -π/2 to π/2 thing. Okay, so what if we don't have like inverse sine of sine? What if we have like inverse sine of cosine or inverse sine of tangent? Then it works out a little bit differently. So we're still going to work from the inside out. So we're going to find tangent of 3π/4. So if you think about tangent of 3π/4, 3π/4 is over here. It's -root 2 over 2, comma, +root 2 over 2. So its tangent is -1, right? Sine over cosine is -1. So when I talk about inverse sine, I'm only thinking on that restricted interval, -π/2 to π/2. So inverse sine of -1 is -π/2. All right, inverse cosine of sine of 5π/6. So sine of 5π/6. 5π/6 is right here. Its sine value is 1/2, right? So I'm going to have inverse cosine of 1/2. So inverse cosine of 1/2. I haven't talked about where cosine is restricted, have I? So we'll talk about that next. Cosine ends up being restricted to 0, from 0 to pi. So where do I have a cosine value of 1/2? It's right here. It would be at π/3. So that would be that answer there. Okay, so the restricted cosine function, again, we have to think about where cosine passes that horizontal line test. So we draw cosine out. So we draw cosine, it starts at 0, 1. It goes like this. Okay, so where does it pass the horizontal line test? It passes the horizontal line test until it gets here. If we go up anymore, then it doesn't pass that horizontal line test, right? So we have to stop at pi. So it's from 0 to pi. So that's the location where your calculator is going to give you, whenever you do inverse cosine, it's going to give you angles that are between 0 and pi. So 0 and 3.14. 3.14159, blah, blah, blah. All right, so whenever you draw the restricted cosine function, I don't want you to draw the right side like we talked about with inverse sine. Instead, I want you to draw the top of the unit circle because it's restricted from 0 to pi. Okay, so lots of things to kind of memorize, making sure that you're making note cards and so on to prepare for the test, but restricted cosine is on 0 to pi. Okay, so when I say inverse cosine of 1, I'm saying on the top half of the unit circle, where do I get a cosine value of 1? It would be right there. So if you need to write it out as equals an angle and think of cosine of some angle equals 1, where is cosine equal to 1? At 0, right? So it would be equal to 0. All right, so inverse cosine of negative root 2 over 2. So right here, where is the x value? Negative root 2 over 2. It's right there. There will only be one location if you do it right. So this is why it has to be on the top of the unit circle. If you did over here, there's actually no places where it would be equal to negative root 2 over 2. But if you did the left side of the unit circle, it wouldn't work, right? So there's only one location. And that number is between 0 and pi. So that number is going to be what angle? 3 pi over 4. Okay, and then inverse cosine of 0.14. This is one that is not a unit circle value, so I will allow you to use your calculator. So we'll get 1.430. All right, so it says by using right triangles, you can write complicated expressions using inverses as algebraic expressions in terms of one variable. So for instance, suppose we want to write sine of inverse cosine of x. Okay, so I don't have a number, I just have inverse cosine of x. And let's say I want to write it as an algebraic expression in terms of x. Well, what we end up doing is we let the inside part, this cosine, we let it be theta. Okay, so I'm going to have cosine, so I'm going to have sine of theta now, because I'm letting inverse cosine of x be theta, which we know that inverse cosine is equal to some angle, right? So I'm letting it be theta. All right, so if I want sine of theta, then I have to rearrange this equation. I have to rearrange this equation that I wrote here. So I want to write it as cosine of theta equals x, more specifically x over 1. So when we use SOHCAHTOA, cosine is equal to adjacent over hypotenuse. So as long as I have theta right here, my adjacent over hypotenuse will be in those locations. So the only thing that I don't know is this other side, this other leg, right? So I need to find it. So temporarily, I'm going to write that as y, just to help me. Okay, so very lightly write y. What I'm going to have is y squared plus x squared equals 1 by the Pythagorean theorem, right? 1 squared. And I want to solve for y. So I have 1 minus x squared equals y squared, and I take the square root, so I get 1 minus x squared. Okay, so that means y is really the square root of 1 minus x squared. So my last thing, so I want sine of inverse cosine of x. Well, we said that inverse cosine of x was this theta. We drew out the picture involving theta. So now sine is opposite over hypotenuse. So it's root 1 minus x squared divided by 1. So it's just the square root of 1 minus x squared. So we have manipulated this equation, or this expression, so that we just get a final answer not involving sines and cosines at all. So it's the square root of 1 minus x squared. So I know that's complicated, so we're going to do it a couple more times. Okay, so let's do the opposites. Let's say we do cosine of inverse sine as an algebraic expression in terms of x. Okay, and what I want you guys kind of get used to is whenever I have something with inverse sine, I'm not always going to draw my triangle like I did above, okay? Because I'm going to kind of need to think about like the signs of these things eventually. So what I want you to draw it as is inverse sine is restricted to this area right here. So we're going to write it. I'm going to write it right here. Okay, and there's actually 2 locations that it could be, but it could be in the first quadrant or the fourth quadrant. But I'll explain this more. So you'll see as things are positive and negative and so on, as we actually have numbers later. But with x's, we'll just start out like this. Okay, so we want to let that inside part. So we're going to say inverse sine of x equals theta. We rewrite that equation. So we have sine of theta equals x, more specifically x over 1. So I'm going to have opposite over hypotenuse, right? Opposite was x, hypotenuse was 1. I find that missing side, which I'm going to call y, by doing Pythagorean theorem. So y squared plus x squared equals 1 squared. So y actually ends up being the same as what it was above, the square root of 1 minus x squared. So that's not y here anymore. It's the square root of 1 minus x squared. Okay, so what that is the length along the bottom of that right triangle. Okay, so then we write our original cosine of inverse sine of x. We said inverse sine of x was theta. Well, cosine of theta is adjacent over hypotenuse. So it's the square root of 1 minus x squared over 1. So it's the square root of 1 minus x squared. Okay, this will not always be the square root of 1 minus x squared. Okay, so number 2. So now I have numbers. Okay, so let's do the same process, but with numbers. And this is why I wanted you to draw it when we have arc sine or inverse sine, write it on the right side. Okay, so we have arc sine of negative 3/5. So the only way, so I'm going to let this equal theta. And arc sine, remember, is sine to the negative 1. So inverse sine of negative 3/5. So what we're saying is that sine of some angle equals negative 3 over 5. So if you remember from lesson 16, if I have a sine equaling a negative, right, this is my y value and my r value, and r is always positive. So it's not the one that's negative, y is, right? So y is going to be negative 3, and r is going to be 5, so it's negative 3. Theta will be right here. Theta is always trapped between the x-axis and your ray. Okay, it's never going to be like right here. I had trouble with that when I was in school. I always tried to draw it in the wrong location. So we need to find the missing side. So hopefully you guys can recognize that that's a 3, 4, 5 right triangle. Okay, so based on its location, and you could do Pythagorean Theorem if you weren't sure, it's positive because it's on the right side of the circle, so positive. So if I want cosine of arc sine of negative 3/5, right, that's cosine of theta, which is adjacent over hypotenuse. Okay, so my answer is 4/5. So a little tricky, but the same thing with numbers. Okay, so let's talk about the restricted tangent function. So remember we talked about sine and cosine being odd and even and so on. So cosine was even, sine was odd, and tangent ended up being odd. Tangent also ends up having the same domain, restricted domain as sine. So if I talk about inverse tangent is going to be on this right side, just like sine was. Okay, and the restricted tangent function, I mean, you can remember what tangent looks like. It looks like this. Okay, so it makes sense that if I want to have it to be 1-to-1, it's only this portion right here. It's none of the rest of them. Okay. So same idea, inverse tangent of 1. And I want you to edit a couple things on this page, actually. So before we even start, number 4, I made it a bad one. I want this to be sine of inverse tangent of root 3 over 3. That's a 3 there. And then this one, let's make it a little bit more interesting. Let's make this a 4. So 4 minus x squared. So I did 1 minus x squared several times, so edit. Okay, so if I have inverse tangent of 1, so tangent is restricted to the right side of the unit circle. I want to know where tangent, so I'm thinking of this as tangent of some angle equals 1. And the angle is on negative pi over 2 to pi over 2. So where is tangent equal to 1? Well, it's equal to 1 when sine over cosine is equal to 1. In other words, sine equals cosine right here. So it's at pi over 4. So pi over 4 is our answer. So the next one, so tangent of arctangent of negative 5. We're going to do the same process that we did with the little right triangles. I know I'm restricted. So I have this inside part is theta. So it's arctangent, which I'll write as inverse tangent of negative 5. So I have tangent of theta equals negative 5. So I have tangent is equal to a negative number. So tangent is not negative up in that first quadrant. Tangent is only negative in the second quadrant and the fourth quadrant. So we're definitely in the fourth quadrant. And when I sketch out this triangle, I want it to be negative 5 over 1. Well, if you remember, this is the y value over the x value, right? So I'm going to have an x value of 1 and a y value of negative 5. And then my theta is right in there. So I need to find this missing side. So I find it with the Pythagorean theorem, negative 5 squared plus 1 squared equals y squared. So when I do that, I end up getting y equals the square root of 26. So if I want the tangent of arctangent of negative 5, I get tangent of theta, which is still just opposite over adjacent, right? So it's negative 5 over 1. So with this, we've learned an important property. If the inverse tangent, inverse sine, inverse cosine of whatever is on the inside, and we have the identical trig function on the outside. So if I have tangent of arctangent, or cosine of inverse cosine, or sine of inverse sine, that's when you can actually cancel them out. You'll get the plain number. Okay, but if you had them opposite, so that the tangent was on the inside and not the arctangent, you cannot cancel those out. Okay, but if you need to, just go ahead and do this work out. So write yourself a note. If inverse is in middle, you can cancel. Okay, so when I say inverse is in the middle, I mean that you have tangent and arctan. They need to be identical trig functions. They can't be like sine and arc cosine, right? You can't do that. They have to be the same. So this one is not, this is not the inverse in the middle. So we cannot do that canceling. This goes kind of goes back to what we talked about at the very beginning, like the 7 pi over 4 one. So let's think about it. 5 pi over 3. 5 pi over 3 is right here. The sine of that is negative root 3 over 2. So I have inverse sine of negative root 3 over 2. So I want to know an angle between negative pi over 2 and pi over 2, right? So restricted to this side. That gives me that. I can't call it 5 pi over 3. I need to talk about its coterminant angle. So what is that? It's negative pi over 3. Okay, and then this one I edited, so it says find the exact value of sine of inverse tangent of root 3 over 3. So you want to say theta is equal to inverse tangent of root 3 over 3. So I have tangent of theta equals root 3 over 3. So remember that sine over cosine equals root 3 over 3. Which is very tricky. So this is where, even in Algebra 2, we talked about this. If you have root 3 over 2 divided by 1/2. So if I had it with the sine and cosine that way, that ends up being root 3. But if I do the other way, 1/2 divided by root 3 over 2, the 2's will cancel. I get 1 over root 3, which is the same if I rationalize and multiply by root 3 over 3. Root 3 over root 3, I get root 3 over 3. Okay, that's the one I want. I don't want this one. I want the one with sine is equal to 1/2 and cosine is equal to root 3 over 2. So I want the one right there. So I have sine of inverse tangent of root 3 over 3, which is sine of theta. We called that theta, right? So when I talk about sine of theta, I want the one where the, had these, oops, that's not root 3 over 2. Hang on. The radius is 1, right? Root 3 over 2. So my sine is going to be the 1/2. And that's your answer. Okay, and this last one, so find the sine of inverse tangent of 4 minus x squared over x. So I made you edit it to 4. So your theta is equal to inverse tangent of root 4 minus x squared over x. So if we sketch it out, okay, that means I have tangent of some angle equals root 4 minus x squared over x. So that's opposite over adjacent. So if I wanted to find that missing side, y, I do my Pythagorean theorem. This is why I wanted to change it from the 1 minus x squared, just because we've done that a couple times. So I have x squared plus 4 minus x squared. squared equals y squared. So x squared plus 4 minus x squared equals y squared. So y squared equals 4. So y equals plus or minus 2. We'll say 2. I'm going to think about why that's not plus or minus. Okay, so then, oh, because it's a radius. Y has to be, y is a length, the radius, so it has to be the positive 2. All right, anyway, so if I have sine of that inverse tangent, that was our sine of theta, right? So sine of theta is opposite over hypotenuse. So it would be this for my answer. Okay. You might get a bonus point on me for that one. Think about that. I'm pretty sure that's right. I had something different on my notes. Okay, so when instructions say find the exact value, you should not use your calculator. So these answers will usually involve pi or square root. So I'll probably have a calculator, non-calculator test. These would be a non-calculator test question when it says find the exact value. Okay, so if I have inverse sine, it kind of goes back to the beginning. Inverse sine of negative 1/2, right? All that is negative pi over 6. It has to be between negative pi over 2 and pi over 2. Okay, inverse cosine of 1. Whenever you see inverse cosine, you draw the top half. Inverse cosine of negative 1, I guess it is. So cosine is equal to negative 1 at pi. Arctangent of 0. So where is tangent equal to 0 on the right side of the unit circle? It means our sine has to be equal to 0, and our cosine has to be equal to 1. So it's going to be at 0. And then these ones say use a calculator to approximate. So hopefully you can do that. Inverse tangent is just negative 1.453. Arc sine, well, that's the same as inverse sine, 0.2447. So let's say I want 3 decimals, so 0.247. And then if you do try inverse cosine of 2, you should get error. This one is not possible because what it's saying is that the cosine of some angle equals 2. And we know that on a unit circle, the biggest cosine can be is 1. Okay, it can't be 2. It doesn't work. So it's not possible. Okay, so hopefully this section was a little bit easier than those transformations. We do have a little bit of like SOHCAHTOA type stuff on the next section. So I know this semester is much harder than last semester, but stay with me. There will be some things that you recognize.